Hey friends, welcome to the YouTube channel all about electronics. So in the last video we had seen the resonance condition for the series RLC circuit, and also we had seen the different parameters like quality factor and bandwidth for this series RLC circuit. So now in this video we will see the resonance in the parallel RLC circuit, and we will also derive the expression for the different parameters like quality factor and the bandwidth. So now let us say we have one circuit in which the resistor, capacitor and inductor are connected in a parallel combination, and in this circuit we have applied some AC voltage source with a variable frequency. So now let us say the current that is supplied by the circuit is I, and IR, IL and IC are the currents which are flowing through this resistor, inductor and a capacitor. And also let us assume that XL is the reactance of this inductor and XC is the reactance of this capacitor. So now whether the circuit is series RLC or a parallel RLC, the resonant condition remains the same. That means when the XL is equal to XC, or we can say that if inductive reactance that is equal to the capacitive reactance, then the circuit will be in a resonant condition. And during the resonance, if you see, the impedance of the circuit will be purely resistive. That means the voltage and current will be in a phase. Also at resonant condition, if you see, the impedance of the circuit will be maximum. So that resonant condition, the current that is supplied by the voltage source will be the minimum, because the impedance of the circuit is maximum. So these are the some of the points which you see at a resonant condition. So now this is a plot of a impedance versus a frequency for a parallel RLC circuit. So as you can see here, at resonant frequency, the impedance of the circuit is maximum, and as we move away from this resonant condition, the impedance will reduce. Now if you see at omega is equal to 0, the XL term will be 0. So the overall impedance of the circuit will be 0. Similarly at omega is equal to infinity, if you see, this term XC that is equal to 1 over omega C will be also 0. So that is the reason at lower and higher frequencies the impedance is minimum, while at resonance condition, if you see, the impedance will be the maximum, and the maximum value of this impedance will be R. So at resonant frequency, the impedance of the circuit will be purely resistive. Similarly, if you see the current versus frequency curve, it will look like this. At resonant condition, the current that is flowing through the circuit will be the minimum. So as you move away from this resonant frequency, the current will start increasing. So now if you see this current versus frequency curve for this parallel RLC circuit, it looks like a band stop filter, because it rejects some frequencies and passes all other frequencies. While in case of a series RLC circuit, we had seen that it acts like a band pass filter, as it passes few frequencies and rejects all other frequencies. And that is the reason this parallel RLC circuit is also known as the rejector circuit, while the series RLC circuit is known as the acceptor circuit. So now let us derive the expression for this resonant frequency mathematically. So now let us once again assume that the current that is supplied by this circuit is I. Now here this current I is nothing but a RMS current. So instead of writing this as IRMS, I am simply writing it as a I. And similarly the voltage here that is indicated as a V is also a RMS voltage. Now let us also assume that the current that is flowing through this resistor, inductor and capacitor are IR, IL and IC respectively. So now if we apply a KCL at this node, then we can write it as a I is equal to IR plus IL plus IC, or we can write it as a V over R plus V over XL plus V over XC. That means V into 1 over R plus, now XL is nothing but a 1 over J omega L, and similarly the XC is nothing but a 1 over J omega C. So we can write it as a J into omega C. So further we can write it as a 1 over R plus J into omega C minus 1 over omega L. Now if you see this term is nothing but a inverse of impedance, which is known as a admittance, and it is denoted by a symbol Y. So we can write this equation as I is equal to V into Y. Now at resonant frequency, the current that is flowing through the circuit is minimum, and to get a minimum current, this Y should be also minimum, and to get the minimum value of this Y, this omega C should be is equal to omega L. So when omega L is equal to 1 over omega C, then the value of Y is nothing but a 1 over R, and we get a value of current I as V over R. So at resonant frequency, the value of admittance is minimum, hence the value of impedance is maximum, and this maximum value of impedance is nothing but a resistor R. So this condition omega L is equal to 1 over omega C is known as the resonant condition. So now let us find out the frequency at which this resonance is happening. So as omega L is equal to 1 over omega C, so we can write it as a omega square that is equal to 1 over LC, or we can write it as a omega that is equal to 1 over under root LC. So this is the resonant frequency in a radian per second at which this resonance is happening. Or simply if we write it in terms of the frequency, then we can write it as a F that is equal to 1 over 2 pi under root LC. So this is the equation for the resonant frequency, and at this resonant frequency the current that is flowing through the circuit is nothing but V over R. That means the circuit will be purely resistive circuit. So now if you see at omega is equal to 0, the value of XL will be 0. So this inductor will act as a short circuit and entire current will flow through that inductor. So for the frequencies which are lesser than omega R, this XC will be greater than XL, as XC is given as 1 over omega C, and circuit will behave as a inductive circuit. That means this current I lags the voltage. While at higher frequencies, if you see, or let us take a frequency omega that is equal to infinity, the XC is nothing but a 0. So for higher frequencies, if you see, this capacitor will act as a short circuit and entire current will flow through that capacitor. So at higher frequencies, this capacitive reactance is a dominant, and at higher frequencies this current leads the voltage. So for the frequencies which are lesser than this resonant frequency, the behavior of the circuit will be inductive, and for the frequencies which are higher than this resonant frequency, the behavior of the circuit will be the capacitive. So now in the last video we had seen that to define the sharpness of this resonant curve, the two parameters are used, which are quality factor and a bandwidth. So now let's see them one by one. So first let us talk about the quality factor. So as you can see here, we have three different curves for the different value of a Q. So now as the value of this quality factor for the circuit increases, the sharpness of the curve also increases, and the resonant curve is getting narrower and the narrower. So we are able to reject a one particular frequency very precisely. And as the value of this quality factor reduces, the curve is getting wider and wider. So instead of rejecting one single frequency, it will reject many other frequencies as well. So now let's find out equation for this quality factor in terms of the circuit components. So now in the last video we had seen that the quality factor can be defined as 2 pi into the maximum amount of energy that is stored across either inductor or capacitor divided by the energy that is dissipated across the resistor. So we can also write this equation as omega into energy that is stored per cycle divided by the power that is dissipated across the resistor. Now we know that the energy across the inductor or capacitor can be given as half Li square, that is equal to half CV square. This term defines the energy that is stored across the inductor, and this term defines the energy that is stored across the capacitor. Now here this current I is nothing but a maximum current that is flowing through the circuit. So now if we write this equation in terms of the RMS values, where IRMS is nothing but I max divided by root 2 and Vrms is nothing but Vmax over root 2, then we can write them as L IRMS square, that is equal to C into Vrms square. So now this quality factor Q we can write it as a omega into C into Vrms square, that is the energy that is stored across the capacitor divided by the energy that is dissipated or a power that is dissipated across the resistor, which can be given as IRMS square into R, or we can write it as a omega into C into Vrms square divided by Vrms square divided by R. So we will get omega into C into R. Now we know that the Xc can be written as 1 over omega C. So we can write this quality factor Q as R over Xc. And also at resonant frequency, the value of Xc, that is equal to XL. So we can also write it as a R over XL. So this is the equation of a quality factor in terms of the circuit parameters. So now as you can see here, the quality factor is directly proportional to the value of a resistance. So as the value of a resistance in the circuit increases, the quality factor will also increase, and hence the sharpness of the curve will also increase. And the curve is getting narrower and narrower. And to define how much it is getting narrower, we use the second parameter, that is a bandwidth. So now this bandwidth is defined as the difference between the 3 dB frequencies. Now if you see the curve of a parallel RLC circuit, at resonant frequency the value of current is minimum. So to get a 3 dB points, we will consider the 2 points where the value of power is doubled compared to the resonant frequency. Or in terms of the current, if we say the value of current is √2 times the minimum value. So these 2 points are the points where the power in the circuit is doubled compared to the resonant frequency. Or in terms of the current, the value of current is √2 times the minimum value. And the difference between these 2 frequencies is known as the bandwidth of this parallel RLC circuit. So now let's derive the expression for this lower as well as the upper cutoff frequencies. So at frequency omega 1, let us say the current that is flowing through the circuit is I1, and this I1 can be defined as √2 times minimum value. Now we can write this current I1 as V into 1 over R plus J into omega 1 C minus 1 over omega 1 L. Or we can write it as a V into 1 over R square plus omega 1 C minus 1 over omega 1 L whole square raised to power 1 by 2. Now this value of I1 is nothing but √2 times I of minimum, and this I minimum is nothing but a V over R. So now squaring up at both the sides, we can get 2 into V square over R square, that is equal to V square into 1 over R square plus omega 1 C minus 1 over omega 1 L whole square. And if we further simplify it, then we will get 1 over R square, that is equal to omega 1 C minus 1 over omega 1 L whole square. That means omega 1 C minus 1 over omega 1 L, that is equal to plus or minus 1 over R. And similarly for the upper cutoff frequency omega 2, we will get another equation, that is omega 2 C minus 1 over omega 2 L, that is equal to plus or minus 1 over R. So now we know that this omega 1 is less than omega R and this omega 2 is greater than omega R. Now the frequencies which are lesser than the resonant frequency, if you see, this Xc is greater than XL, or we can say that 1 over Xc is less than 1 over XL. That means omega C is less than 1 over omega L. So if you see this equation, in this equation the sign of this 1 over R should be negative. That means omega 1 C minus 1 over omega 1 L, that is equal to minus 1 over R. And similarly for this second term, if you see, the omega C will be greater than 1 over omega L. So we will get omega 2 C minus 1 over omega 2 L, that is equal to 1 over R. So now let's solve this first equation. So if we simplify this equation, then we will get this equation. And further if we simplify it, then we will get omega 1 square plus 1 over RC into omega 1 minus 1 over LC, that is equal to 0. So now this equation will have 2 roots. So the roots of this equation can be given as minus 1 over 2 RC plus or minus under root 1 over 2 RC whole square plus 1 over LC. Now here the frequencies cannot be a negative, so we will only consider the positive term. That means omega 1 that is equal to minus 1 over 2 RC plus under root 1 over 2 RC whole square plus 1 over LC. And similarly we can derive the expression for omega 2 that is 1 over 2 RC plus under root 1 over 2 RC whole square plus 1 over LC. So in this way we have derived the equations for the upper as well as the lower cutoff frequencies. Now bandwidth can be defined as the difference between this upper and the lower cutoff frequencies. That is nothing but a 1 over 2 RC minus of 1 over 2 RC. That is nothing but a 1 over RC. So in this way the bandwidth can be defined as a 1 over RC. Now if we multiply these two equations, then we will get omega 1 into omega 2 that is equal to 1 over 2 RC whole square plus 1 over LC minus 1 over 2 RC whole square. That is equal to nothing but 1 over LC. So in this way we will get omega 1 into omega 2 as nothing but 1 over LC, and this 1 over LC is nothing but a omega r square, that is the square of the resonant frequency. So in this way omega r can be written as under root omega 1 into omega 2. So this is nothing but a relationship between the upper and lower cutoff frequencies with a resonant frequency. So earlier we had found out the equation for the quality factor Q as nothing but a R over XC, that is R into omega C. Now here according to the equation of bandwidth, delta omega is nothing but 1 over RC. So we can write this equation as omega over delta omega, which defines the equation between the quality factor and the bandwidth. That means Q is nothing but omega over delta omega. Also if you see, this Q is nothing but omega into CR, where omega is nothing but a resonant frequency. And we know that omega r is nothing but a 1 over under root LC. So we can also write this quality factor Q as under root C over L into R. So this is how this quality factor can be defined in terms of the circuit parameters. So now at resonant frequency, if you see, the inductor current IL can be defined as V over XL. So now at resonant frequency the voltage V can be written as I into R. That is I into R divided by XL. And if you see this term is nothing but a Q. So we can write this inductor current I as nothing but a Q into I. Similarly, if you see the capacitor current, which can be written as V over XC, and we can write it as I into R over XC. Again this term is nothing but a Q into I. So in this way if you see, at resonant frequency the value of a current that is flowing through the inductor and capacitor is magnified by the value of this quality factor Q. So this parallel RLC circuit is known as the current magnifier circuit. While if you see the series resonant circuit, the series resonant circuit is known as the voltage magnifier circuit. So in summary, if you see in a parallel resonant circuit, at resonant frequency the voltage and current are in a phase. Also the impedance of the circuit is maximum, and the value of this maximum impedance is nothing but a R. That means the impedance at resonant frequency is purely resistive. As the impedance is maximum, so the current that is flowing in the circuit is minimum. Also this parallel resonant circuit acts as a band stop filter because it rejects one particular frequency and passes all other frequencies. And this parallel resonant circuit acts as a current magnifier because at resonant frequency the current that is flowing through the inductor and capacitor is multiplied by the value of a quality factor. So these are the equations which we have derived for the parallel resonant circuit. So I hope in this video you understood what is the resonance in the parallel RLC circuit. So if you have any question or suggestion, please let me know in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.